Let's think about this example. So if Fubini's theorem tells me that if I have a continuous function on a sufficiently nice region in my domain, then I can perform the multivariable integral by taking iterative integrals, and I can switch the order around. Then I can use that to my advantage, because maybe one order of integration is better than another order of integration. And we're going to see that here. Let's consider the function sine of x divided by x defined over the triangular region in the plane bounded by the lines y is equal to 0. So I've got y is equal to 0 right there. I've got y is equal to x right there. And I've got x is equal to 1. So we are trying to integrate this function right there. So even though it's only a function of one variable, we can still think of it as a function of two variables, except it just is constant in the y variable, right? It's a cylinder. Right, so I've got this function existing over top of this region right there, and I want to integrate it. So the integral over the region R, that triangle, of my function, which technically doesn't depend on that y, but we can think of it as it's still there. Now, by Fubini's, I can perform iterative integrals because sine of x divided by x is continuous on that region. So I'm going to integrate in the x and in the y. And let's do, what do I want to do first? Let's do the x first. Now, if I integrate in the x first, that's me drawing horizontal lines in my region. So the x variable is going to go from this point there, which is on the line y is equal to x. So x can be described with the y value of y. And we're going to integrate over until x is equal to 1. All right, now the bounds for the y integration, I'm going to take these horizontal lines and I'm going to integrate them from y is equal to 0 to y is equal to 1. All right, let's see where this gives us, or what this gives us. Let's tell ourselves what the function is. Sine of x divided by x with respect to x first, and then y. So this is really as far as I can go, because I'm trying to integrate sine of x divided by x with respect to x. I don't know what that is. Sine of x divided by x with respect to x. I mean, what's an antiderivative of sine of x divided by x? I have no idea. So if I can switch my order of integration, maybe it's going to make the problem a little bit easier. So we can also say that this is going to be equal to the integral. So I'll just switch colors. If I take the same region and I integrate in the y variable first, then my bounds for the y integration is going to be, So I'll integrate my function with respect to y first and then x. The bounds for the y is going to be from 0 to x. And then I'll take these red lines and I'll integrate horizontally in the x direction from x is equal to 0 to x is equal to 1. All right, let's see that this actually gives us an answer. So we'll integrate iteratively our function sine of x divided by x. Now notice sine of x divided by x integrated with respect to y, that's just a constant. So I need to give sine of x divided by x a y. So this is going to be sine of x divided by x times y evaluated from, and this is in the y at first. So evaluated from y is equal to 0 to y is equal to x. All right, so sine of x divided by x times y when y is equal to 0, I end up with a sine of x. Or I might have misspoke there. When y is equal to x, I end up with sine of x. And then I'll subtract sine of x divided by x times when y is equal to 0, but that's just 0. And now you can see that I'm not going to have any problems here. I can find an antiderivative of sine of x with respect to x. That is going to be minus cosine evaluated from x is equal to 0 and x is equal to 1, which gives us minus cosine of 1 minus a cosine of 0 minus cosine of 1 plus a 1. And that is going to give us, so let's just make an approximation here, about 0.46. Cool. So one order of integration didn't really give us anything, but we could use the fact that Fubini's theorem tells me that I can perform those iterative integrals in any order that I want to. And the other order actually gave us a result.